Hello, everyone. I am delighted to introduce our next speaker, Üzeyir Saçıkay, who has graduated from Boğaziçi University with a double major in physics and mathematics. And he's on his way to Ludwig Maximilian University in Munich to study theoretical and mathematical physics. Üzeyir, I wish you the best for your future academic journey. And Üzeyir and I have been working on kind of like a hot topic, deep learning and neural networks. And he is going to talk about its mathematics today. So Üzeyir, take it away.
Bu kadar ya. Bu kadar ya. So, hello everyone. I want to thank Ulgen for the kind introduction. As Ulgen mentioned, we study deep learning and neural networks, which is quite a hot topic nowadays. And I'm quite sure you keep hearing about machine learning, AI, deep learning, neural networks, or any set of words that vaguely mean the same thing. So I will be talking about like a general intuition about these concepts and give like a general picture rather than focusing on the details. So I hope that I can give you some intuition about, because I think this would be like much more understandable for someone with mathematics background. So without further ado, let's begin. And I think, yeah, the first natural question to ask would be like, why should we care about neural networks in the first place to begin with? And I think, yeah, the best answer is we can use them to do quite interesting things. And some examples include, we can use them to predict the three-dimensional structure of all like distinct proteins on Earth, which is around like 200 million. And we can do that with atomic precision, because like proteins have this like quite huge and complex structure, and it's been a long and open problem in the field of biology, and recently they were able to do this. And then we can maybe use neural networks to be able to identify each zebra, even in different pictures. We would know that it's the same zebra just by looking at its stripes pattern. And then maybe we can use this information to build a database. They did this in Kenya, where they built a database of each zebra, and then they used that for ecological research or wildlife conservation purposes. And then we can use neural networks to accurately translate like complex sentences and texts between over 100 languages. And then finally, we can use neural networks to write a program that can recognize cats just based on the picture. And that's what we will be focusing on today. So our aim is to create an app that consists of cat pictures. So I would just open the app, it would show me a cat picture, and I would tap on it and it would show me another cat picture. Now it's not clear how is this related to neural networks, but we will just go step by step and discover along the way. So yeah, the first problem is we need a lot of cat pictures because such an app would be quite popular and we would anticipate like huge amount of users. And so how can we find that many cat pictures? Well, the first approach would be to just, go and manually search, and as much as we find, we would upload it into our app, but that would be quite exhausting to do such a task by hand. And also we might forget that we downloaded the same picture a week ago and then downloaded it again, that would lead to duplicates, and we don't want that. Well, another approach would be to just, write a script that would just go to Google and then search cats and then download whatever comes up. And the problem with that approach is that how would we know that all the pictures that come up when you type in cat are of the cats? And to give an example, this is one of the pictures that comes up when you go to Google Images and type in cat, because like the brand is named Cat, and so that approach wouldn't work either. But maybe we can build on that approach and then write another program that would just go through the downloaded ones and then pick out the pictures that are really of cats. So it would look something like this, like whenever we give it a picture, it will tell us whether it's a cat or non-cat. So yeah, that sounds like a plan, but we have no idea how to do that. Like we have, it's because it's something a human can do, but we have no idea how can we teach a program to do that. So maybe we can outline like a general learning program, not specific to writing a program, but like a general approach for learning. And maybe it would look something like this, like we would make guesses. And then after we make those guesses, we need a way of like measuring our error, how accurate our guesses are. And once we get that done, we need to find out the changes we need to make in our guess making process to be able to make better guesses. And once we get these down, we can just repeat this process until we get the like satisfactory guesses, until we're good at guess making. So this sounds like a good plan, but we still have no idea how to like apply this plan to in the context of computer science. So it seems like we are stuck, and it's a good idea to go back to the history and see what people did to deal with this problem. The first significant breakthrough came in 1943 when McCulloch and Pitts invented what is called the perceptron. A perceptron is like a quite simple like binary decision makers. We give these like binary inputs, and then we assign these weights based on the importance. And just based on this weighted average, it decides an output. And it just does this by checking whether this weighted average achieves a certain threshold or not. So it's influenced from the like biological neurons, because they work kind of similar to this. They're much more complex than this, but it just checks the inputs, like the impulses from the synapses, and then it fires or not based on whether that impulse achieves the activation threshold or not. But a simple perceptron on its own is quite simple, and we want to be able to make more, complex decisions and perform more complex tasks. And maybe to make things more complex, we can just connect these perceptrons end to end and create this like network design. So, and another advantage of using this design is we are like kind of dividing our task into subtasks. Each layer would deal with something, get a result, and then give that result to the next layer, and then that will deal with it. And then, it would just be an iterative process, and each subtask, each layer would get better at doing that specific subtask. And in the end, we would have like a collaborative network. But the problem with perceptrons is like we need an automatic way of doing this thing. Like we don't want to go and check, like tune those weights individually. And even if you want to tune the weights, it would be impossible to do with perceptrons because they are discrete, like they either fire or not. And if we try to tune them, like maybe we make a small change in one of these weights and that somehow flips the output of this one, then that would cascade throughout and that would lead to significant changes for the rest of the network, some sort of like butterfly effect. We don't want that. That would be like quite difficult. That would make it quite difficult to tune these weights, because we want to be able to like make small changes, and then that would lead to small changes, some sort of like a continuity between these weights and the output. And actually, as I mentioned, continuity, we can think of this whole network just like a single function, because it's just composed of different functions. And in the end, it just takes some inputs and gives us an output, and in between there are compositions. So we want these dependence on the weights to be continuous. And that's not the case with perceptrons. So maybe to deal with that discreteness, we can just remove the threshold condition altogether and then put it to the other side of the equation and get this like affine transformation design. So we wouldn't have the problem of discreteness anymore. These are continuous, but this creates another problem, because when you compose affine transformations, you have another affine transformation. And there is no point of using a network design, because in the end, we can just represent it using a single affine transformation, like a single perceptron. So finally, we can make a final modification where we use the output of our affine transformation as input to this nonlinear function. We introduce this nonlinearity to our network, and that things make much more complex. And in the end, we get this like final function that looks like this, as composed of many single functions. So in the end, this might seem like a small modification, but actually it gives us this quite powerful existence theorem, this added nonlinearity, which says that the set of neural networks is dense in the set of continuous functions over the complex domain K. So what this means is that we can arbitrarily approximate any continuous function over a compact domain. And it just gives us a guarantee that there is a network out there that can recognize cat, that can translate between languages, and that can like spot zebras and then recognize in different pictures. But it doesn't tell us anything about how. Like, it just gives us an existence, but it's still reassuring. So getting and in the end, we have this like after we fix that structure, that design, we have this like a forward flow of information, which is called the forward pass. So each input gets like we take the weighted average of these inputs, and then that would be our linear output or affine output. We would use them in our nonlinear function, and that just gives us the whole output of this unit, and then we would just send it to the next layer. So the whole forward pass process looks like this. So yeah, getting back to cats, neural networks seem promising for this kind of task, but how can we integrate them into our learning program, that the plan that we sketched out earlier? And let's just go step by step. So we need first figure out a way of making guesses using neural networks. And we can do that by just feeding these images into a neural network and just propagate, like forward propagate, just use the forward pass that I just laid out. And the final output we get would be our guess. And we need to somehow decide on the weights, and we can just to get things started, we can just choose them randomly, as we hope that we will find a way of getting the optimal weights in an automatic way. So yeah, making guesses is kind of dealt with using forward propagation. And then we need to like measure on the error of our guesses. And to that end, to be able to measure the error, we need to know what the output was supposed to be, because we want to compare the true labels and the predict labels. So in order to be able to do that, we can just label some pictures by hand and use that set of images as training data. So using this like labeled images, we can calculate our loss, our error on those images. It would be just like a metric, which gives us a distance between true and the guessed labels. It could be anything. It depends on what you're trying to do. We have like a lot of freedom on what this loss function is supposed to be, but it just needs to be consistent. Because it's like a measure of error. We want it to be a measure of error, and then we can just take the average error over the whole training data. And our main aim is to make this as small as possible, since it gives us a measure of error. So once we get the accuracy of guesses out of the way, we can focus on finding out the changes we need to make to making better guesses. And as I said, that's just boils down to finding a set of weights with lower loss. And to do that, we can just use our knowledge from calculus that the gradient of a function at a point gives the direction of steepest ascent. Because in the end, loss is just a surface, like it's a surface over the set of weights. And we want to find the, a local minimum, just going over the surface. And we can use the fact that gradient gives us the direction of steepest ascent. We want to go in the direction of steepest descent. So we would just use the negative of that to update the weights. So it seems like we have a plan for to finding out the changes we need to make, and then we would just update all the weights using this rule. So we call this update the back propagation, because in the first part we were going like forward, the information was flowing forward and we were getting the output. And then in the second step, we use the output to calculate the update. So it's sort of like we're going backward in the second place. That's why it's called back propagation with gradient descent. And then we need to repeat this process until we are satisfied with the guesses. But yeah, and that just boils down to iterating until the loss is minimized. As I mentioned, loss is just a function, and it might have like several local minima separate, like scattered around. And how would we know which one is better than the other? And it turns out that some are more preferable than others, and that preference depends on how it generalizes. Because you see, we use this training data, we manually label some pictures, and in the end, it's just a sample of just like millions and billions of cat pictures, and we want our model to be able to generalize just based on the how it performs on training data. And like to make that more concrete, if our model like focuses too much on the sample, it would just be tricked by the noise in the sample. So it would try to get this like, really sharp decision boundary between two sets. Like say we are trying to find a separation between these stars and circles. If we focus too much on the noise, it would be like a quite complex boundary, and it wouldn't generalize. If we have like another set with similar distribution, it might perform quite badly. But we need something that can decide that these are noise and just ignore them. So this would generalize much better because it focuses on the general patterns rather than specific nuances and noise. So we want to find those minima that can generalize better. And to be able to test generalization performance, we can just manually label more images and then designate that as our test data. And then we would just check our performance on training and test. So what we do is we train our network using the training data and then test its performance on the test data, because it has never seen the test data before. So how it performs on the test data gives us an idea how it would perform on things that it has never seen before. So we want the performance of our model to be good on both these sets. So that looks something like this. Like we have all these models, like this model class, which so all of these like correspond to different set of weights, different set of architectures, and etc. Some of them perform quite good on the training data, and some of them perform quite good on the test data. But we want this intersection between the two, because these one might be overfitting. Like they're learning the training data quite good, but maybe that's not what we want in the end. We want to be able to predict general patterns. Like we want to be able to predict what a cat is just based on a picture. We don't want to focus on the limited sample we have. And the outline, then we would add this step to our outline. And that sort of concludes how to learn using neural networks. Now, there are a lot of details that I haven't mentioned here. This is like just some sort of general picture of how learning would go. And maybe some future work would include like using these speech recognition networks to be able to recognize meows and then differentiate between cats just based on the sound and the manner. And then maybe add a feature that lets users add pictures of cats as people love showing pictures of their cats to other people. But that creates a problem of its own, because these new pictures that people took on their own would be quite different than the ones we used in test and training. Because it might be blurry when you take a picture, or people may, I don't know, like use many other like different angles than we could find on the web. And so how would we integrate to our system? How would we integrate to our learning process? So those are some things to think about after we laid out the fundamentals. And yeah, that sort of concludes my talk.